Welcome everyone to the Sound Demixing Challenge Town Hall. This is the second time we're hosting this challenge. And in today's Town Hall, we have 4 challenge organizers who will be covering important and different aspects of the challenge. We have Gordon from MERL who will be giving us a challenge overview and introduction, and also sharing some details about the ongoing phase and perhaps phase 2. Then we have Igor from Moises.ai, and he will be giving us a walkthrough of the data set. After that, we have Giorgio Fabbro and Stefan from Sony R&D, who will be doing a deep dive for both the tracks, music demixing track and cinematic sound demixing track. After that, we'll have a Q&A session and then some feedback session. So that's the agenda for the day. I will let my first speaker of the town hall go ahead.
All right. Well, thanks everybody. I'm excited to be here and kick off the town hall. But so I'm just going to introduce the challenge very quickly, and then we'll get into some of the more exciting details. But you know, as everyone probably knows, this idea of sound demixing or source separation, whenever I think about it, it always goes back to the way our human brains work, which are really, really great at source separation, right? And people kind of refer to this as the cocktail party problem. And this is the idea: you can be in a cocktail party, a really loud room with a bunch of people speaking, and really your brain and your ear can focus on that one person you're actually listening to. And so next slide, please. Kind of the goal of audio source separation then is, how can we design an algorithm that can really kind of replicate that type of behavior? And really now in 2023, when we design an algorithm to replicate that behavior, we really wanted to use AI. And so really what source separation ultimately is we have some mixed signal, like a music song, and we want to separate it into its components, things like vocals, drums, bass. And unlike a lot of AI audio related tasks, such as like speech to text, where we're just labeling the content, in this case, we actually want to signal at the output that we need to listen to. And there's source separation has been used in many different ways. I've grouped it on this slide here into 3 main fields of application. The one that's probably gotten the most research attention throughout history is speech. And, you know, so that's separating 2 people speaking at the same time or removing background noise from speech. And that's what's shown in the middle. And then we have the 2 tracks that we're kind of focusing on in this sound demixing challenge, which on the left, we have music source separation. And in this case, we have a song and we want to separate it into 4 components: vocals, drums, bass, and other. And that's the MDX track of the challenge. And then on the right, we have the cinematic sound separation, or speech music sound effects separation, and that's kind of the cinematic sound demixing track. And next slide, please. And so when I'll say kind of, you know, this idea, I'll use cinematic sound separation maybe as my kind of straw man task, I guess, for explaining this here, because we at MERL, we got interested in this idea of cinematic sound separation because, you know, I think probably a lot of you have had this experience. You're watching a movie and maybe you have a hard time understanding like what people are saying. And then, you know, a car crash or an explosion happens and it like wakes up the baby. And so it would be really nice if you could have a better volume control that could just adjust the sound more clearly. Or what happens to me a lot is I'll be watching a movie and I'll hear something really interesting in the score, and I'll be like, oh, that sounds like a really great piece, but I can't hear it because there's a car engine, you know, going overhead or something. And so it would be really cool if you could kind of just adapt that control online. And that led us to create this data set called the divide and remaster data set to do cinematic sound separation. And what we did here is we just took the open source data sets available from the internet. One from Freesound, we used that to get sound effects. We used LibriSpeech, which is an open source corpus of people reading audiobooks to get speech. And then for music, we took data from the Free Music Archive, and we designed some, you know, kind of crude mixing process to try to more or less approximate from this stuff something that sounded kind of like a movie. And we created a mixture. And then, and this is kind of a typical source separation pipeline, whether you're working on music or whether you're working on speech. I mean, these data sets of the isolated sources change, but the process is the same. And then the mixture goes through a deep neural network, and you estimate the different sources that you're interested in. In our case, a sound effects track, a speech track, and a music track. And then you compare those to the ground truth sources that actually created the mixture using some type of evaluation metric. And during training, you back propagate the error through your deep neural network, and that's how you train. But then you also use at inference time or during the challenge, we use this evaluation metric to actually rank the system performance. And so really you'll hear more from many of the other speakers about the different data sets and the different tracks in the challenge, but really ultimately the difference between the tracks and the leaderboards is what data you actually use to train your model. And for all tracks and leaderboards, the evaluation metric used in the challenge is the global source to distortion ratio. And that's essentially just the error between the estimated waveform output by your model and the true waveform. And that's averaged over stems, all the different source types, and then the number of songs and clips in the data set. So next slide, please. And so I think probably if you're here, you're probably already convinced that source separation is important. It's used from everything from karaoke, people use it a lot in hearing aids, music education. If you want to learn an instrument and you can somehow cancel out the one you're trying to play, that could be super valuable. Before I was at MERL, I worked making audio post-production products for people who work in recording studios, and source separation was a very valuable tool for that. And I just wanted to show this video real quick, which is created using, I'm not sure if we have sound. If not, that's okay.
Sound not audible?
I'm not hearing it. Yeah.
Okay, 1 second. Let me see.
TV shows, and commercials. In these examples, we interpolate between various mixing configurations.
A little bit in the video. Yeah, to here.
What the hell is that? Everyone's got a gimmick now.
So really what you can see in this video is this is actually using the baseline model for the CDX challenge.
Awesome, dude.
And we just kind of built this interface that allows you to move between the different separated sources and focus on whatever it is you're interested in.
Oh, God. Hey, buddy, I think you lost this.
And then we tried it on a lot of stuff. This one is pretty good. This is a TV commercial.
Hi, Phil Swift here for Flex Tape, the super strong waterproof tape. That can instantly pack. No ordinary tape.
It's triple thick adhesive, virtually welds itself to the...
Okay, that's probably
but Flex
good.
Tape grips on tight.
If you want to. I encourage everybody to watch this. As it goes on, we tried it on Jimmy Fallon, on cooking shows, all kinds of neat stuff we found on YouTube, and it's pretty amazing. This kind of relatively simple model that's the baseline in the challenge works pretty well, and you can do all kinds of fun stuff with it. So yeah, you can go on to the next slide. Yeah, I encourage everyone to maybe watch that offline because I think the video and audio wasn't synced very well.
Yeah, that's the message that we have in chat saying that the video and audio shifted, so it looks like it's not working. But yeah,
yeah.
I'll
please watch it online. It's a fun
I'll share
demo.
the link in chat and also in the resources after the town hall, so you guys can watch it offline.
Yeah. Okay, and just for me wrapping up, I guess, on these last couple slides is so source separation has been around and studied for a long time, and there have also been kind of challenges in source separation for a long time. So I think starting in around 2007, there was this signal separation evaluation campaign, and these things went on for many years. And then, as deep learning came on the scene, there was a data set called MuseDB 2018, which provided kind of an open training set for deep learning based source separation. And that really sort of moved the field forward a lot. And then 2 years ago, Sony and AIcrowd, amongst others, also organized kind of the music demixing challenge, which was the direct predecessor to the current sound demixing challenge. And I think I have one more slide that just goes over kind of the mechanics of the challenge. And so for those who haven't participated before, the challenge takes place over multiple phases. And I think, at least as I understand it, the main purpose of the phases are to give participants the chance to avoid overfitting too much on the hidden data sets. So if we released all the hidden data at once, you could fit your model and tune it, very well to that. But by releasing it in these pieces, it allows you to not be able to do that, but also test your generalization ability over the multiple phases. So we're currently in phase 1, and as of right now, algorithms are ranked using 1/3 of the hidden data. And then starting in a few weeks, I guess, on March 6th, we'll move to phase 2. And in this case, the rankings will be based on 2/3 of the hidden data. And this is for both tracks. I think this split is true for both tracks. And this phase 2 really gives you a chance to see if you have overfit your model too much to kind of the phase 1 testing data. And then 2 weeks before the challenge deadline on May 1st, the participating teams will be frozen. So nobody has the chance to swoop in at the last second and do something crazy. And then ultimately the final ranking with the prizes will be determined on the full hidden test set. And all right, so I think that's all I have for my portion, and I'm happy to move on.
If you have questions for Gordon, you can leave them in chat. We'll be taking all the questions after all the speakers are done presenting. So if you have any questions, please leave them in chat and we'll pick them up later.
Hello all. I would like to thank Gordon for the nice introduction to the source separation challenges and so on. So I'm Igor. I'm the head of data science at Moises.ai. So at first, my next slide, if you please advance here. I'm gonna briefly talk about our contributions to the sound demixing challenge. So long story short, we saw the latest music demixing challenge of 2021, and we really appreciate the initiative, especially want to congratulate Sony and AIcrowd for bringing that challenge up, and especially connecting researchers to the companies that aim to use this sort of system. So this year we decided to join forces with them, and our special objective contributions. We helped to raise the price for the MDX track. We're gonna help with the subjective evaluation, especially for the applications for the MDX track, which is something that we really think about. Okay, we all know that SDR is not a perfect metric. So these years we would like to also apply some sort of subjective evaluation. We also helped with the marketing during the pre-launch at this beer. We sponsored this beer the last year, so we did some marketing during the pre-launch of the sound demixing challenge. We're also gonna provide a data set for you to use during the challenge. So the short-term contributions like this, the Sony Moises sound demixing data set. I think there's someone with the microphone open. So. And our long-term contribution that we plan to release after the challenge has ended is the Moises.db, which I'm gonna briefly talk about in my next slide. So with Moises.db, we aim to support the scientific community with more data. We know that it's a bit hard to find licensed data to use while building the sound separation models. So we also want to address a bit of the lack of instrumental diversity. We know that MuseDB has the 4 stems, which is awesome, but we also want to add more. So it kind of makes sense at this moment to have guitars, piano, keys, and strings separated as well. So the Moises.DB so far has 203 tracks, which is about 12 hours of the raw sources. So we provide we only provide the sources, but we do organize it in a hierarchical format. We're going to release the dataset after challenge has ended, and we're also going to release a Python package along with the data that parses the metadata and do on-the-fly stems mixing. And it's going to be licensed with Creative Commons license. So the taxonomy that we built is basically consists in these 11 main stems, which are vocals, bass, drums, other guitar, other plucked, percussion, piano, keys, strings, and wind. So for each one of the stems, we have another layer that I haven't added because otherwise it wouldn't fit in the slide, but have another layer of raw instruments. So yeah, you can go to the next slide. So we're looking now at from the 203 tracks, we're looking now at the numbers of tracks that has the vocals stems. For example, like almost all of them has the vocals, drums, and bass. Most of them have the guitar, piano, or keys, and some of them, not all of them, of course, have the strings, wind, and other instruments. So as in the rightmost table, you guys can see that there is this hierarchical representation of the stems and the source. Of course, I limited the number of entries in this table, otherwise it wouldn't fit in the slide, but you guys can see that the drums, we have the cymbals, drums, drum machines, full acoustic. For guitars, we have separated acoustic guitar, clean electric guitar, and distorted electric guitar as well. And that's one of the reasons that we could build together with Sony. I think Giorgio can talk more about it in the next slides of how we could insert label swapping and also the bleeding to create these two problematic data sets. So next slide, please. So this is a representation of the genre of the data sets. So we can see that the data set lean towards most popular music, rock and pop, which is, well, not that great, but also kind of represents the majority of the songs we have available. And we can also see that the stems, somehow they seem to be balanced, at least for bass, drums, guitars, and vocals. It seems to be balanced among all of the genres. And of course, the other less common stems, they have a bit of shift there. And we also have bossa nova, which is kind of cool, but we have only some for that. Artists and genres. So I've anonymized the artists for the presentation. The dataset will be released with all this information. But we noticed that some artists, like the artist V, has a large amount of tracks in the dataset. So, well, at least they vary in genre. We know that genre is also a very subjective, kind of subjective classification of genres. There is some looseness in there, but we can see that at least for the most recurrent artists in the dataset, we see 3 genres in there. So that's one of the reasons that we requested our provider to add more tracks to the dataset, so we have a more balanced dataset by looking to the artist amount of tracks. I think I have one more. No, I don't have. That's it. I would like to thank you, Sony and Mitsubishi and AIcrowd once again. And that's it.
Thank you so much for that. We'll now move to the MDX track, where Giorgio will be presenting.
Yes, thanks. So hi everyone, I'm Giorgio from Sony, and first of all, thanks Gordon and Igor for the nice introduction. We are now going to go deep into the music demixing track, and we will look at all the information that is already available publicly on the website, but also on some more details on what exactly these data sets, for example, that we provide for the challenge are created, how they are created, and how they can be used. So the music demixing track is basically a continuation of the previous music demixing challenge. So the formula is the same in the sense that the submissions are expected to separate a song into the 4 tracks, the 4 common tracks: bass, drums, vocals, and other. And we assume that other as a category contains any other instrument that is not bass, drums, and vocals. This time, though, while in the music demixing challenge in 2021, we had 2 leaderboards where the only distinction between the 2 was the amount of training data that was allowed to use for those submissions. This time we go beyond standard formulation for music source separation, and we actually look and focus at the issue of robust music separation. By robust here, we means that the models that the participants train are supposed to be able to be trained even with data that contains some errors. It contains some inconsistencies. The thing is, so this is particularly realistic when we consider the fact that normally with neural networks you need a lot of data. And by collecting a lot of data, ensuring that this data is coherent, so different songs have exactly the same and correct partition in the stem identities or in the presence of mixture stems, so stems that have signals from multiple instruments. This is very difficult, right, to ensure. So especially when dealing with supervised supervised learning, the quality of the labels that we use to indicate the identity of an instrument, for example, is very important. And the more data we add to the training pipeline, the more likely it is that this data contains some mistakes. And also the more the models will be impacted by it. So we want to bring the focus of the community to this particular issue, and we devote, therefore, 2 of the 3 leaderboards of the music track to this issue. We consider 2 types of errors in the dataset. One is called label swaps, one is called bleeding, and we define label swap basically as a stem which has the name that does not necessarily match the signal it contains. So we might have a track labeled as drums, but it actually contains also the recording of a bass guitar. On the other hand, the bleeding is defined as a perturbation of a track with the filtered signal of another instrument. Think of it in the music studio. You might have the singer recording their track, and they wear headphones to listen to the remaining part of the song, so the accompaniment. And some signal, some sound from the headphones can still be heard outside and is captured by the microphone. So in the end, the vocals recording will contain both the voice of the singer and also a softer and filtered version of the remaining accompaniment. Another case, another instance would be when you want to record drums and bass, and you want to have a performance by the 2 musicians at the same time. So they want to play together. So the microphones that are used to mic the drum set might pick up some of the signal from the bass amplifier, which is particularly tough to isolate, being at low frequencies. So in the end, you will have in the recordings of the drums also a portion of the signal from the bass. So in the end, we define one leaderboard, leaderboard A, for submissions that are trained on data which is corrupted with the first kind of error, so the label swaps. Leaderboard B is the same, but data corrupted with bleeding. And finally, leaderboard C is submissions trained on any data, and this is identical basically to the leaderboard B of the previous challenge, the Music Demixing Challenge in 2021. One important item to remember is that every submission to leaderboard A and leaderboard B is also automatically considered for leaderboard C. So in the end, you don't have to focus, you don't have to submit only to leaderboard C in order to participate to leaderboard C. Whatever you do in the music demixing track will be also considered in leaderboard C, and you have a chance also there to basically be listed in the leaderboard. Next slide, please. Yeah, so let's look a little bit more in detail into the training data that we have released. Now, we start from the clean dataset that Igor just described, this Moises.ai. They will release the clean dataset at the end of the challenge. At the beginning of the challenge, we released 2 versions of this data, which has been corrupted with these 2 types of errors that we refer to. So SDXDB23 label noise contains label swaps, and SDXDB23 bleeding contains bleeding. Now, the way we simulate these corruptions, both for label noise and for bleeding, is based on some knowledge that is gathered during an internal data labeling activity. We have access to an internal storage of music data that we train our systems upon, but this data has these issues, suffers from label noise, suffers from bleeding, and so on. So by going through this data, we collected some statistics over the occurrence of these errors, depending on, for example, which instrument identity that is. And we created, therefore, probabilities that given that there is an error, how that error is going to be. For example, the probability of having signal from the bass guitar in the vocal stems, right? That has a higher or lower probability that in the vocal stem you find signal from the drums. And this is easily defined based on the occurrence of bass inside vocal stems in our internal data. So we simply counted the amount of times that the number of times that we had to correct something like that. And as a consequence, we obtained with this probability. And the simulation that we did on the Moises.ai respects this knowledge that was gathered. Now, there is one item which is particularly important to consider when talking about label noise, which is the fact that the original data from Moises, the Moises.ai, contains, as Igor showed, more than 4 stems per song. So we have a much finer grained level of classification of the stems. For example, you might have a difference between strings and brass, although for the purpose of the challenge, strings and brass belong altogether to the other class. So when creating the datasets for the challenge, we had to group multiple stems together in order to comply with the format of Moises.ai 18 and to the format of the challenge as well. And it's important to notice that the corruptions that we talk about, both label noise and bleeding, are applied before grouping the stems. What does this mean? It means that, for example, if we want to apply a label noise corruption on the strings stem and bring it to the drums, in the end, you will have the drums track in the dataset for the challenge, which contains both drums and strings. Okay, so it's not enough to simply change the identity of that stem manually to solve the issue. It's actually a mixture stem in that case. It is therefore not possible to manually correct the stem labels by simply changing the identity of, so the file name, basically. And it's also important to notice during the challenge, we will not provide too detailed information about which stems contain the corruptions. For the label noise in particular, a certain percentage of the data contains this label noise, while the remaining part of the data is actually fine and it doesn't contain these issues. Also, at the same time, the simulation of the bleeding is done by applying a varying and very often random amount and type of effects. So we take the signal from, in this case, strings, and we make it bleed into the drums track. But while doing that, we apply some signal processing techniques with random parameters, with random type of effects, and so on. So that it's not so easy, it wouldn't be so easy to simply remove the bleeding component by simple signal processing. Next slide, please. Right. Just to clarify maybe one question that I saw on the chat earlier, then the datasets that we will provide during the challenge are these 2 datasets that I just spoke about. also the SDXDB23 label noise and bleeding. So leaderboard C will not have a specific dedicated released data set this time. You can simply use any data you have. Now, talking about the test data, all leaderboards are evaluated on the same taste data, MDXDB21, which is the one that we used also in the previous edition of the Music Demixing Challenge. It's important to notice also that this data is not corrupted with label noise or bleeding, so only the training data is. And the model that you train is supposed to be able to be robust, basically, with respect to those mistakes. And in the end, when evaluating the performance of your model, we will do it on clean data, so as to really measure the effective performance of your model. Now, Gordon already went through the different phases, so I don't think we have to go through this in detail. The image, the table that I report here is the list of songs that are present in the hidden test set MDXDB21. This figure is actually already public. It was released when we released the paper about the Music Demixing Challenge in 2021. So for reference, you can also take it from the Frontiers Journal. Next slide, please. Yes. Let's talk about prices. This is definitely interesting. The total price pool for the MDX track is of $32,000. And they are divided into the 3 leaderboards, so that leaderboard A and B get $10K each, and leaderboard C gets $12K. One important aspect is something that Igor already mentioned, is the bonus prize in the leaderboard C. This is $2K. This bonus prize is something new in the Music Demixing track. It wasn't present in the Sound Demixing track. And it was possible exactly thanks to Moises, because we agreed that basically the separations of the top K submissions will be analyzed by a panel of experts, music producers, people in the music industry that work in music production professionally. And these people will be appointed by us, and their job will be to determine which separations sound the best via a listening test. So it's not just about SDR, signal to distortion ratio, as an objective metric, but it's also going to be about how good it sounds. And this perceptual evaluation will be carried out after the end of phase 2. So once we get the results on the whole test set, we will select the top K submissions in leaderboard C, and these will get basically the possibility of being evaluated by this panel of experts. I think I have just 2 slides at the end to finish my part about the baselines. Now, we offer a pool of baseline models that you can use to kickstart your submissions. Basically, you don't have to start from scratch, right? You can take one of these models and do whatever you want with it, but at least you don't have to start from scratch. Let me start from leaderboard C, because there is where we already have some leaderboards available. We have 2. One is CrossNet UMX trained on 100 hours of data, and the other one is the popular Open and Mix model, which was, I believe, also present in the Music Demixing Challenge 21 as a baseline. So this was in turn trained on 500 hours of data. Maybe something new for you, there will be some baselines coming also for leaderboard A and B. And in particular, they will be Open and Mix, Demux, and MDXNet. All of them trained on one hand on the XDSDB23 label noise, and on the other hand, and the XDSDB23 bleeding. In particular, the Open and Mix is already trained, and we are uploading it, so it will come really in a few days. Demux, we have Alexandre de Fossé, the original author of Demux, which is currently training these models, and they will come in about a week. And the MDXNet, we have Wichern, one of the original authors, that is currently training as well these models, and they will also come soon. So keep an eye on the leaderboards, especially for leaderboard A and B, because new baselines will appear soon. And also, if the number of submissions keeps growing, if we see that there is really a lot of interest in the track, then we can also think of adding more. There's nothing stopping us, really. Okay, the last slide, I believe. Yes, some tips and tricks. what can you do in order to really start experimenting, at least in the MDX track? Actually, these ideas are also valid for the cinematic track, so you can reuse the same ideas very easily. One would be of blending models. By blending, we mean that you take two models and you combine their outputs somehow. You can be a linear interpolation, so basically a mixing, or it can be also something more elaborate, but at least you don't have to retrain a model from scratch. I mean, this is effectively model ensembling. The history in machine learning is quite long, but you can try to stretch this as much as the inference timeout allows. Right now, you also have access to GPUs during inference, which is a novelty with respect to the previous edition of the challenge. So you can really maximize the amount of power that you can give with the networks, networks being plural. Another idea would be to fine-tune the baselines. Of course, if you have access to more data, you don't have to necessarily train from scratch, right? You can just take a baseline which was already trained and fine-tune on your own data. Be careful though, this is allowed only in leaderboard C. So leaderboard A and B are for submissions that are trained exclusively with the datasets that we provide. You cannot use any other data, not even MOSDB18. And finally, avoiding residual signals. This is quite nice because the sum of the outputs of your model doesn't necessarily correspond to the original mixture. And so there is some residual signal that was not taken out of the mixture. But the sum of the target ground truth that we evaluate against, their sum actually corresponds to the mixture. So if your network forgets a portion of the signal, then that is definitely going to be considered a mistake. And therefore your STR score will be penalized. So try to reuse this residual signal and assign it somehow to the various outputs, to the four outputs of your network, so as to minimize the chances that your network basically leaves something out of the mixture. Okay, this is it by me. Good luck with the submissions, and thank you all for participating. I'll leave the stage now to Stefan for the cinematic.
Then I can directly take over. So welcome also from my side. So Giorgio already talked about the music, the mixing track, and now it's about the CDX track. So first about cinematic source separation. So the task for you is to separate into dialogue, music, and effects. And maybe if you know more about movie audio production, there are actually really those three tracks that are used basically during the process of movie production, called DX, MX, and FX. And it has many applications. So Gordon already showed nice examples. You can use it for upmixing of old movies, going from stereo to Dolby Atmos, for example. And also quite an important use case is dubbing of a movie in a new language. And there you want to remove basically the dialogue and then basically redub the dialogue in a new language. And for the CDX track, there are two leaderboards. Leaderboard A are for models that are only trained on the DNR dataset, and more on this on the next slide. And leaderboard B is for models trained on any data. So if you have like your private dataset that you can use, or you, for example, want to make use of music data from MOSDB18, for example, then you can really make use of it and add it to your training data set and, for example, fine-tune the cocktail fork model that you will hear more about in a minute. So on the next slide, it's first about the hidden test data. So for ranking the submissions, there's also a hidden data set used, and it's really a data set which comes from real movies. Okay, so it's not something that was just made for this competition, but it's really real movies that have been used. Some statistics here. There are 11 movies. One is a demo movie, and then there are basically 10 hidden movies where the clips come from. And again, basically, we did a split by movies into 3 parts. First split is used for the first phase. Split 1 and 2 is used for the second phase. And then for the final leaderboard, again, we will use all movies. So the evaluation, as you can see here on the right, like in this small font, is done in the same way as for the MDX track. And maybe interesting for you is that originally we started with 40 movies, but we had to remove some because we really wanted to make sure that the clips have enough variety, and also we kind of filtered out, for example, clips where we don't have enough energy in one of the three sources, like dialogue, music, and effect. So therefore, at the end, we end up with 156 clips, and they have a total length of 20 minutes. So an average clip has a length of 11 seconds. And they come in 44.1 kilohertz, which is the same format as the divide and remix dataset, and are in stereo, so 2 channels. Maybe interesting for you, if you haven't seen it yet, there is like, there was one question about really how we split between effects and music. Please have a look here. And if there are more questions about the dataset, please feel free to ask. But we really tried to make sure that there's only dialogue, only like human sounds in dialogue, only music in the music track, and then everything else like car noises, gunshots, and so on, these are in the effect track. So we really tried and listened to all those things to make sure that there's really, the classes are well defined. And one other note is we cannot give more details about the movies themselves, because at the end you could fine tune, right? You could just purchase the DVD or get the audio somewhere from the internet and try to start to fine tune. So therefore, at the end, it's 10 movies that you could buy somewhere, but you cannot, we cannot tell you, at least right now, more. Maybe then for when the challenge is over, we will tell more, but right now we can't. There is one demo. If you could please go back, Sneha. There is like one movie that we have selected as the demo sample to also give you feedback. You don't have to play it, Sneha, but if you have some time, feel free to listen to this short movie. It's a short movie that was created by the Sony group to kind of showcase all the newest filmmaking technologies that they have. So like with the newest film camera, and they also played with virtual production a lot. So this movie was shot at the same time in 2 different locations in the US and in Japan, which is really quite fascinating. And it was shot in front of a clear crystal wall, which just gives the scenery of the house, and it looks real, although it's just has been shot in a parts of the movie have been shot in a studio. So I can also recommend the behind the scenes, because then you can really see what was done in order to make this movie. Okay, if you, yeah, please go one slide back, Sneha. And just here you have the demo clips. So if you do a submission, maybe you have seen that you can listen like to one clip from Kilian's game. And if you use like the link, the first link that you can see here, this is exactly the same part than in the movie. Maybe that's interesting for you to see, then also listen to your separations and then see also the picture with it. So if you please change to the next slide. Yeah, about the baseline. So MERL released a nice model, a cocktail fork model, which you can use as a baseline. And this is a model which is trained on the divide and remaster dataset. So you can here find the 2 links, one to the original model repository, and then the second link shows you how, or guides you to the baseline repository. Just 2 comments for you. The first one is about the divide and remaster dataset. There's an old version and a new version, and please make sure that you use the newest version, because it's just better to use. And if you use the link that is given here on the slide, then you will end up with the newest version. And the second thing is about the maybe you have seen in the baseline code, there's some weird scaling going on. And that's just because the original model was trained with scale invariant SDR, but we evaluate with global SDR, as Gordon also mentioned. And therefore we need to estimate the correct scale for each estimate. And right now it's done in this way. As you can see here, it's just the least squares estimate of the amplitude. And maybe that's not the best thing to do. And there's maybe room for improvement. But right now, this is how it's implemented, and that's the reason why there's this scaling on going on, because of this, the way of how this cocktail fork model was trained. So on the next slide, now there are some ideas for you to get started, what you could do. And the first thing is that the cocktail fork model itself is single channel because the divide and remaster dataset is single channel. Maybe you have already noticed. And there are basically two things that you could do. One is, as it's done right now, you just apply the cocktail fork model channel-wise. And then what you could do is afterwards, you could use a post-processing, which is aware of the two channels that you have. So for example, you could use a multi-channel Wiener filter. And here is one implementation that you could use from Fabian. Maybe that's a way to start with. Another thing what you could do is you could really invest data augmentation strategies for the cocktail fork model. So you have the dataset. You have this dataset, which is single channel. And now you could think of, okay, I could, during creating like the mini batches for my training, I can use panning, for example, and create a stereo track from the single channel audio data that I have. And many, many more stereo effects there are that you could use, and which could help at the end to make your model really exploiting spatial information. And this should also boost the performance of the model. A second problem that you will encounter a lot when you work with dialogue for movies is that they contain emotional speech. Simplest case could be just someone shouting, and that's something that is not normally in the normal speech data sets that we use for training. So a simple way would be that you could add vocals from source separation dataset for music. You could look into emotional speech datasets. There are quite a few that you could use. And also what you could, just as a simple starting point, what you could do is you could take the vocals model, say, for example, from UMX, from the baseline, and just blend this with the speech, with the dialogue model that you have. And this should already help and give better performance. Then for the scale recovery, as already mentioned, the current scheme, I think, is not the best, but it works. But feel free to explore better ways how to estimate the scale. I could imagine, especially for effects, there's a problem because you have very little energy in the estimate, and then it will be very noisy, the scale that you estimate. So there could be better things that you could explore, or you train like the model with a different loss function. So feel free. There are many things that you can explore. Then you can also investigate other network architectures with the divide and remaster dataset, and so on and so on. So there are many things that you can do. You can try to improve the model. You can try to improve the data, or both. Okay. Then one last thing, just about if you're new to such kind of a challenge. What can you do if you encounter submission failures? There are basically two things that we wanted to tell you. One is something that you should always do before you do your submission, and something then, okay, it went wrong, it didn't succeed, what can I do afterwards? So before, there is, in every starter kit, there's this local evaluator. So, and you can see the command how to run it here. So you should always run it and just make sure that this doesn't produce any error. And if you don't have yet the data that is used for this local evaluation, just check this Python file, and there's like a description how to get the data that you need to run this local evaluator. Then make sure that you have all the Ubuntu and Python packages added, because that's needed at the end for the Docker container that you build. And also, third thing is, I think it's always maybe easier if you just start from something that is already working. So you could just start from an existing baseline, use this code, and then maybe you just replace the parts with your model, and then tweak it. But maybe that's easier, because then you see how to really add all the requirements that you need for your model. What can you do when your submission failed? There are log files provided in the issue that you can see on GitLab. And just check there for keywords like package not found, unknown command. These are like indicating where there's something wrong. What you could also do is you can locally create the Docker container the same way as it will be used for the evaluation. And there's like, if you follow this link, there's like a way how to do this. And then, I mean, if you have spent quite some time and you can still not figure it out, feel free also to ping Deepam. He's kind of taking care of all the infrastructure, and then he can look into your submission. Okay.
Thank you so much for the presentation, Stefan. We have a pretty active conversation happening in the chat. So I would request the organizers to just give a look at the chat, and we can perhaps respond to the queries. So it's quite a lively discussion that's happening between the participants. Let's start from the top. Malcolm asked a question regarding the data set for leaderboard C. So I think that's already clarified into separate presentation where any data set can be used for leaderboard C. If any of the organizers wants to jump in and discuss that more, they can.
Yeah, no, so exactly as you said, Sneha, so there is no release for leaderboard C this time as a new data. You can use any data you want. So even the data that we released for leaderboard A and B, in principle, you could use. I mean, it's corrupted, but still is extra data. And there is no limitation in leaderboard C for the data you want to use. We simply don't release anything new.
Nabaru,
Yeah, so
sorry.
Just to add to Giorgio's answer, the reason why we're not going to release the Moises.DB during the challenge is because you can use the clean version to kind of trick about leaderboard A and B. So the idea is to use only the corrupted versions for the leaderboard A and B. So that's why we're gonna release the Moises.DB afterwards. The challenge hasn't been.
Okay, thank you for that clarification. Nabaru has asked a question regarding baselines for leaderboard A and leaderboard B. So I believe Giorgio covered it, but maybe we can go through that again. Also, Nabaru also follows up with another message about there seems to be a lot of overlap between the two corruptions if there are label errors before grouping, that is artists wrongly labeled, or combine two stems and just name them as one. Thus, label noise might also have some kind of effect in bleeding. So I guess Giorgio and Igor might be the right people to answer this.
Yeah, so about the baselines for leaderboard A and B, yes, I already mentioned them in my presentation. And by the way, sorry it's taking this long, but we will get them out there as soon as possible. So you will have also some baselines to start with, like very soon. Regarding your comment on the type of corruption, you are absolutely right. So label noise and bleeding are very related to each other in the sense that you could see as a label noise as being a bleeding that has no filter, no change in volume. It's just a direct copy. So it doesn't have any practical, real, let's say, occurrence per se in the studio when you record. Bleeding is more towards the recording aspect of music, while label noise in the production, post-production actually, of music. But still, from a signal processing point of view, they are very much related. So in the end, your comment is correct. Keep in mind, though, that bleeding occurs very often in the training that we release, and it's much more than label noise, I would say. And also the component that is made to bleed into the other track has been strongly processed, filtered, and also the volume is reduced and so on to make it a bit realistic with what happens in the studio. So overall, conceptually, you could think of it as the same kind of corruption, but in practice, what you get in the two training data sets is different.
Okay, I hope that clarifies. Okay, I'm wondering, Navarro has you can unmute yourself and ask a question too. It doesn't have to be exclusively on the chat. Yeah, but Navarro has a follow-up message saying, I'm wondering if it won't be a bit of GPU time saving if we could train once for both the leaderboards.
Okay, I see what you're saying. I would still argue that we shouldn't allow you to do that because the corruptions in the two data sets happen only on a portion of the data, and they appear in different portions of the data. So by combining the dataset for leaderboard A and a dataset for leaderboard B, you would actually get two versions of each song, possibly one clean. And that's not inside sort of the task that we require. So in the end, I hear you, but no, unfortunately not.
He also has questions regarding the evaluation and scoring. So he mentions that median to aggregate the score might be better than mean because it might be more affected by outliers.
Maybe Stefan?
Yeah, I can answer. So for BSS Eval version 4, there is exactly this problem because it's like a frame-wise evaluation. And we could have frames where there's like very little energy for one source and there's large error. And therefore, we have to use a median kind of averaging. But here we really made sure that, and we use this global SDR, and we have for every stem, there's enough energy. So there's not really an outlier there. So the problem is only happening if we have, and that's happening for frame-wise evaluation, when we have frames where there's basically one source not present or very little in energy. Then we can have like very low SDR scores, and then it's better to use a median global SDR.
He also has a question regarding the labeling for the CDX track, whether the track ground truths were manually mixed or real movie tracks have been separated by some model.
No, these are really from the Pro Tools sessions. So they are really the original tracks without using any model. So they are like clean separations.
Sandesh has a question regarding cleaning practices in pre-processing step. So he says we obviously cannot use data outside of the given data set for source separation, but as a pre-processing step, can we use other models for data cleaning?
Yeah, so I think there was already a question in the discussion forum regarding this. And in principle, no, you are not allowed to use pre-trained models on other data to clean the training sets, because that would amount to use other data. It's implicit, but it's what it is. Keep in mind that what we want to do so the whole reason why we have these two leaderboards is that we want to bring the focus towards robust training and training robust models. And this is a whole, I would say, there's a whole branch of literature research in machine learning that attempts to do this, just not with audio data. And we simply would like to see some approaches maybe inspired by those models that maybe are not so focused on audio data being applied on audio signal processing in this sense. So in the end, while using a pre-trained model to clean the data might be seen as the most immediate way to get to a nice result, it's not the purpose of the challenge in our view. On top of that, even if it's not, think of it in this way, one way would be to train a source separation model on MuseDB 18, which suffers much less from these issues, and then have that separation model to run on each individual stem in the corrupted datasets and clean it. That would be seen as a way of cleaning the data source pre-processing step. You don't submit your source separation model trained on MuseDB to the challenge, but you are still using it eventually. So in the end, we don't allow even this situation, because that would be sort of, it doesn't respect the rules in terms of utilization of data. Whether you train the model that you use your own or you use a pre-trained one, it still uses other data than the one that we provide.
So I guess that answers even the follow-up question that Malcolm had regarding the MDX track for leaderboard A and B. The same reasoning applies, but for leaderboard C, you can use any training data.
Yes.
Gordon shared a second version of the cocktail folk and model tray, second version of the data, but I guess Malcolm is not able to access it. Let me see if I can open the link. Okay, I seem to be able to see it. I guess I'll be sharing it, updating this on the discussion forum and also on the respective challenge page soon. Nabaru says in the CDX track, since effects have low energy, seems like it's an incomplete query. Would you like to unmute yourself and ask the question?
Yeah, sorry. So this was in relation to the mean and median discussion. So yeah, the global SDR in the MDX track, the mean is fine, as Stefan said. But since the CDX track, the effects have low energy, won't it kind of skew the mean? No? Yeah, that was my kind of question.
Yeah. But as I said, we really made sure that we have a certain minimum energy in every effect track. Otherwise, there could be problems. I fully agree, but we really made this sure, and therefore filtered out clips. Yes.
Okay, thank you.
Great. Do we have any more questions? You can either unmute yourself or you can send a message. Malcolm, if you're not able to access the link, I'll share the link in the resource section of the town hall. And yeah, okay, so cool. It seems like you're able to access it now. But I'll be updating the link at the relevant places soon. If we don't have any more questions, then I'll move to the last part of this town hall, which can you share? Yes, I'll be sharing the slides and also the video recording of this town hall by Monday or Tuesday. So this is a challenge feedback part where, as both from the AIcrowd side and also from the challenge organizer side, we'd like to know what are some of the main pain points that you as users are facing, either in the submission process or in the evaluation or even in creating your first solution. So if there are certain blockers or if there's some things that are not very clear or a common occurring error that we could address, we'd like to really hear from you guys. You can, again, if you don't want to unmute, you can drop it as a message in the chat, or you can just unmute and share that with us. This gives us a chance to fix any of the common issues that you might be facing and make the process of this challenge smoother for you. Could a small validation set be made available for corrupted tracks? I don't know.
Yeah, that's an interesting one. So we thought about this, and so in terms of realistic settings, having a clean validation set is definitely possible. So there's no problem with that. One thing that I might suggest, so of course we already released the complete corrupted version of Moises.ai, right? So we don't have any more songs that we can release now to aid as a validation set. So that's not possible from our side right now. If we allowed you to use extra data as a validation set, so clean data for a validation set, then we would also need to somehow give you recommendations on what to use, and that could skew your results in the end. One thing that you could do is, for example, to select out of the training set that we provide some songs that are actually clean and use those as validation set. That is definitely an option, and I would say it's the easiest one because it respects every rule and it gives you, in the end, the result that you want. You're validating on clean data, which is the same as the test data, and at least you don't get wrong signal from the validation part.
CDX submissions page is not available. Okay, I'll look into that. I'm not sure why that is the case, but yeah, that should be fixed soon if that error is happening. Are there any more feedback? Maybe you can also share, if you don't have any critical feedback, you can also share something that you have really enjoyed about the challenge so far.
Yeah, I guess the best part about the challenge is that when you're listening to results, you actually get to listen to some music. So that keeps things interesting.
That is
rather than just staring at like loss curves and stuff, you can actually like listen to some music.
Malcolm has a feedback regarding the AIcrowd repo Docker. I will forward this query to a member from the technical team and have it just fixed or responded. If this is not addressed in next 3 to 4 days, you can post this again on the discourse forum, and I'll make sure that you get a reply on that. All right, great. Any other feedback?
Can I ask one more question? Sorry.
Go ahead.
Yeah, I'm wondering if anybody tried like mixed precision or half precision training, because I've tried quite a bit and I don't seem to be able to like get it to work. So if you have any tips on that, it would be really helpful. And like I've not even seen any papers like use like mixed precision training for the results. So yeah, I'm just wondering about that.
You mean like the normal PyTorch AMP, right? Automatic mixed
Yeah,
precision.
yeah.
Okay. So for LSTMs, we don't see any problems. I think UMX you should be able to train just out of the box. And for the conf models, it should. Sometimes there are problems. Yeah. But most of the time it works out. But for UMX, for example, I think we never have seen a problem.
Okay. So did you actually try that? Like
yeah.
Okay, I see.
We use it, yes. And as I said, sometimes there's a problem. You have to be careful, but normally it works.
Okay.
So if you use the CRED scaler, which is part of the AMP, it normally works.
Yeah. So like the spectrogram function and all is kind of excluded from is done in full precision and then.
No, this was normally part of the pre-processing pipeline. Okay, it depends how you implement it. Normally only the model is wrapped into mixed precision.
Okay.
Interesting point. Yeah. So this I never tried about like computing a spectrogram in 16 in half precision. This I don't know. Maybe others have experience. I don't know.
Okay. Thanks.
If we don't have any more questions or feedback, I guess we can end. Okay, what's the GPU memory required to train MRXNet for CDX? We have a new question from Yukiya.
I can answer. I think the version we released used a 48 gigabyte GPU with that batch size, but I think it should scale as a function of batch size reasonably well. So if it's smaller, a 12 gigabyte card, you could reduce the batch size by a factor of 4. And if you wanted to be sure to match our recipe inside of PyTorch Lightning, there's a I forget, taking the multiple batches is built in to simulate a larger GPU. I'm blanking on the term for that right now, but it's built into PyTorch Lightning, which the MRX code uses.